Hello physicists, in this video we're going to be looking at constant acceleration. Since that's the situation in which most motion happens. We can approximate a lot of motion with constant acceleration. So it's very important to analyze objects moving with a constant acceleration. And we have a set of equations that we use for constant acceleration. And there are two equations that basically govern all of one-dimensional motion. Okay? And these are known as kinematics equations. Kinematics is just the study of motion. So we're going to be deriving the kinematics equations. Okay, now, these only work for constant acceleration. If acceleration is not constant, these don't work. These become really wrong. Okay, so we have to assume the acceleration is constant. So that means the average acceleration is equal to the actual acceleration. Okay, so that's just the rate at which velocity changes with respect to time. And we're going to be using magnitudes because we're going to be applying numbers to these. So you can either use the vector notation, but we're going to be deriving in terms of numbers, magnitudes. Okay, now the acceleration is the change in velocity or speed with respect to time. So that's Vf minus V naught over delta time. Okay, now if we multiply both sides by delta time, we get Vf minus V naught equals A times delta t. And isolating Vf, we get Vf equals V naught plus A delta t. And delta t is just written as t for convenience. So that's our first kinematic equation. The second one's a little harder to develop, but not super hard because acceleration is constant. Now, the average velocity, we're going to be focusing on average velocity, and because that's what we're going to be using in order to derive our second equation. Now, the average velocity is equal to the change in position or the change in time. Okay, so that's just xf minus x naught over, we'll just write t. Now, because the acceleration is constant, we can also write the average velocity as just v naught plus vf over 2. V naught plus vf over 2. Because the acceleration is constant, the velocity is just a straight line. And that allows you to just come up with this expression rather than any other expression. So this is our average velocity. So we have two different ways of expressing average velocity, and what we're going to do is equate them to each other. So we have xf minus x naught over t equals v naught plus vf over 2. Now, vf is, we can use our first kinematics equation and substitute v naught plus at over 2. And what we get is 2v naught plus at over 2. All right, sounds good. And we can just write this as v naught plus at over 2. Now we have delta x. I'm going to just write this as delta x. A little cleaner that way. Equals v naught plus at over 2. That means that if we multiply both sides by t, we have delta x equals v naught t plus 1/2 at squared. And this is the second kinematics equation. And these two equations literally can be used to solve all one-dimensional motion problems with constant acceleration, of course. And one of the most important applications comes with falling objects. And we're going to be investigating falling objects, and we're going to do a couple of practice problems with these equations later. So just to recap, our two main equations are Vf equals v naught plus at, and delta x equals v naught t plus 1/2 at squared. Excuse me. And you might have heard of some other ones. There are like 3 other ones that can also be considered kinematics equations. But those other ones can just be developed in tandem by using these two equations in tandem. So you could, by using just these two equations, less equations to memorize and more understanding of what's actually happening. Thanks for watching. We're going to be continuing with kinematics next time. Thanks for watching. See you next time.